Hello info person, this is Anton, and today we're going to be discussing this new research and this new discovery that seems to challenge the most fundamental laws when it comes to physics. And here we're talking about the fundamental rule of the universe. Nothing can travel faster than light. And that's of course something we've been told for over a century. Yet in this recent study published in 2026, researchers potentially confirmed that sometimes some things, and specifically dark points within light waves, can actually travel just a little bit faster than light, even though the light itself travels at the regular speed. Which, though might sound a little bit unusual and kind of bizarre, is actually something that was officially predicted quite a while back. And so in this case, let's actually discuss exactly what this means, what this particular experiment was able to achieve, and what this means for us when it comes to understanding the entire universe. But to understand why this is significant, let's first discuss why we always thought that faster than light speed, or superluminal motion as it's also known, is essentially impossible. And this is of course the basis for the Einsteinian special theory of relativity. Here the speed of light in a vacuum is roughly 300,000 km per second and represents the absolute maximum in the entire universe. And though obviously light can travel slower than that in different types of media, it cannot travel faster. And the reason for this is mostly twofold. First, when it comes to different objects, like for example spaceships, since this object now has a mass, as it approaches the speed of light, its momentum increases in such a way that it would actually require infinite energy in order to achieve 300,000 km per second in velocity. In other words, for different particles and for anything containing mass, it just becomes impossible to even reach the speed of light. Which is why when sometimes particles like the OMG particle that strike the planet at extremely fast velocities, everyone gets really excited because nobody has any idea how such a particle could achieve such a high speed. Here we're talking about velocity of about 99.9999999% of the speed of light. But the second reason, which is a little bit more important for physics, is that the speed of light is also tied to the idea of causality. So basically here, if you could send a signal faster than light, you could theoretically then send information backward in time. And this creates a causality paradox. Here, the effects happen before causes, and the entire logic of the universe kind of goes out of the window. Nothing makes sense anymore. And so because of this, the overall scientific consensus as of today is that basically nothing, no matter, no energy, and of course no information, can ever cross that particular line when it comes to the speed of light. And well, here we're talking about this exact value. Okay, so let's discuss these dark points. And that's basically what this new research is about. And so here scientists whose paper you can find any description, instead of focusing on the matter, decided to measure something referred to as optical phase singularities, sometimes also referred to as optical vortices. Something that you can see visualized in this image. And here we basically have to think of light as not just a straight line or some kind of a laser, but instead as a kind of a wave that can twist and ripple, creating a shape that resembles something like this. And at the very center of this twist, the light waves cancel each other out completely and create a point of zero intensity. Essentially a tiny hole of total darkness embedded within the light. Here's actually another way of seeing it, if you were to look at this as a cross-section. And this is something we've known about since the 1970s. As a matter of fact, physicists like Michael Berry and John Nye predicted that these unusual dark holes technically could behave like tiny particles. As a matter of fact, they even predicted that under certain conditions, these vortices could even outrun the light waves around them. In some sense, kind of similar to what you might observe on the surface of water, when some kind of an eddy might actually move a little bit faster than the current on the river. In other words, just like the eddy right here, light also contains these dark spots formed by the light wave itself. And here's actually a really cool demonstration and recreation of these optical vortices that helps you visualize what this might look like. And well, the thing is, until now, this was mostly just a mathematical theory, because these events usually happen on scales way too small and way too fast for any of us to see. As you can see here, the counter is in femtoseconds. And so we just didn't have enough technology to verify any of this or to make this happen. But more recently, there have been some breakthroughs in specialized microscopy techniques, and specifically a technique referred to as ultra-fast transmission electron microscopy, also known as UTEM for short. And this is not your typical microscope. Here it actually uses pulses of electrons in order to film light dynamics at a resolution of 3 femtoseconds. That's 3 quadrillionths of a second, which of course in theory now allows us to see some of these events. And so for this experiment, researchers used a material referred to as hexagonal boron nitride. And in this material, light couples with atomic vibrations in order to create a kind of a light sound wave. In physics, these are known as polaritons. Basically a kind of a hybrid between a light photon and the matter excitation. And in this case, these polaritons are useful simply because they move about 100 times slower than light in a vacuum, which allows us to sort of slow down background light and then allows researchers to observe the dark vortices as they move. So it's kind of like observing actual light in slow motion. And so here what they've discovered was fascinating. As two vortices of opposite charge approach each other, they essentially cancel out or annihilate and then accelerate. And the study measuring these vortices reached unbounded velocities, suggesting that for a brief moment, some of these little holes moved faster than the speed of light. And that's actually comparable to the predicted values. And so here data show that on average, a lot of these tiny dots were approximately 1.04 times faster than the speed of light, or approximately 4% faster, which of course confirms those predictions from 50 years ago. But this obviously does not break physics. In other words, this does not violate the rules of the universe. And the reason why is in what's actually moving. Because in this case, first of all, these dark points are massless, and they're not made out of atoms or even photons. As a matter of fact, these are just geometric features of the wave pattern. And because they contain no mass, no energy, and carry no actual information, they don't really violate Einsteinian rules. In some sense, this is actually similar to how a shadow or a laser spot can move across a distant object such as our own moon at speeds faster than light. So here no physical object is actually traveling any distance. It is just a shadow. Which brings us to the next question. So if nothing here is happening and if nothing is being moved, why does this matter? If these points carry no information, why should we even care? Well, because first, it confirms that the laws governing these vortices seem to be universal. For example, we see very similar singularities in things like superconductors, superfluids, or even other fluids, and specifically flowing fluids, such as those formed during different cyclones. And so by understanding how they move in light, we can then better understand how they behave in exotic materials, which might one day lead to new types of electronics or energy systems. Second, this is also a huge breakthrough for microscopy. The ability to map nanoscale phenomena and at femtosecond speeds presents scientists with a very powerful technological tool to see how nature behaves at some of the most elusive moments, something we could never see before. And so here this technique can now help us study a lot of processes in biology, chemistry, and even atomic interaction, helping us solve a lot of mysteries from different fields. In other words, here it's the microscopy technique that's one of the major breakthroughs. But I guess even more importantly, when it comes to these optical vortices, technically there are some potential physical applications. For example, because some of these beams do carry momentum, we can use these holes to trap stuff inside. In other words, they can be used to trap and rotate microscopic particles without any physical contact. And so by creating and controlling these tiny holes, we can technically use them in a lot of different microscopic devices. Likewise, for astronomy, a device referred to as optical vortex coronagrapher has already been proposed in order to block intense light from different stars and in order for astronomers to see very, very dim objects next to stars. In other words, for direct observation of different exoplanets, even when the star is very bright. And so here optical vortices can actually be used to block a lot of the starlight. Likewise, we can technically use this in a new type of optical communication, and in this case by sending multiple data streams, and by using these topological charges, theoretically it can actually increase bandwidth infinitely, allowing us to transmit so much more information in the same amount of space as before. And so at least theoretically, some of these bizarre structures and these very strange light holes can one day become useful in a lot of different fields, which is also one of the conclusions from many of these studies. This is potentially a new field in optics, where many of these vortices can now be used because of their stable particle-like nature and because technically they can carry data if we design them the right way. But the team behind this study is planning to now do this in 3 dimensions. In other words, even though this demonstration has now been just in 2D, now they want to discover if there is even more complex behavior if you try to visualize this in 3 dimensions and not just a flat surface. And while this doesn't mean that we're going to be building faster than light spaceships or even communicate at faster than light anytime soon, it's still exciting to know that even inside the light itself, there is this darkness that seems to travel faster than individual photons, outrunning them in the process, which is once again what you're technically seeing right here. And so here we have this reminder that universe, even with its very strict rules, sometimes contains these loopholes that once in a while we tend to discover. But at least for now, that's all I wanted to mention. We'll definitely discuss this more if there's some additional discoveries, but until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.